Welcome back. In this video, I'm going to solve exercises 1 to 4 of chapter 1. First exercise, I stated as a lemma and I asked you to try to prove it on your own. So we have a subset A of a metric space and we have to show that A is totally bounded if and only if its closure is totally bounded. Okay, so suppose first that A is totally bounded. So we go back to the definition. So let epsilon be a positive given number. Now, we know from a remark in the lecture that if A is totally bounded, then A can be covered by finitely many balls of radius epsilon. Okay. Now, if you look at the union of the corresponding closed ball, the union of the closed balls of center xi and radius epsilon is a closed set. It's a finite union of closed set. So, and of course, it contains this union. So it contains A. But A bar is the smallest closed set containing A. Therefore, this union of closed balls contains A bar. Now, of course, the closed ball of center xi and radius epsilon is contained in the open ball of center xi and radius 2 epsilon. Okay, so we succeeded in covering A bar with a finite union of open balls with center, of course, in A bar because the xi are in A and therefore are in A bar. Now, since 2 epsilon was arbitrary, this just proves total boundedness. Okay. If you want to have precisely epsilon here, then you have to take epsilon over 2 here. But once again, it's not important. If you find any constant times epsilon, it's fine. Okay, now conversely, suppose that A bar is totally bounded and that epsilon be, again, a positive given number. So, therefore, I can cover A bar by a union of balls of center in A bar and radius epsilon. Okay, now of course we could say, well, this contains A, but the centers are not in A. The centers are in A bar. But this is not a big deal because if xi is in A bar, then we can find an element in A as close as we wish to xi. Okay, so for each I, we can find an element yi in A whose distance to xi is less than epsilon. This is the famous characterization of the closure of a set. So if you like, A bar is really glued to A in some sense, cannot separate them. So therefore, if x is in A, then therefore x is in A bar, and therefore it's in one of these balls. So it's in some ball of center xj and radius epsilon. Okay, for this j, choose yj, as we said, such that dxj yj is less than epsilon. Therefore, the triangle inequality tells us that the distance between x and yj is less than the distance between x and xj plus the distance between xj and yj. So epsilon and epsilon to epsilon. Okay, therefore, we took an arbitrary element in A, and we proved that it is in some ball of center yj and radius 2 epsilon. Therefore, A is contained in the union, this finite union of balls of center ya in A and radius 2 epsilon. Okay, and since epsilon was arbitrary, this precisely means that A is totally bounded. Okay. So the point is that to prove that a set is totally bounded, the centers of the ball should be in the set. Okay. So this concludes the first exercise. This was lemma 1.1. Exercise 2, we say that a topological space is separable if it contains a countable dense subset. Show that a totally bounded metric space is separable. Okay, an example of a separable space, of course, is R, although it's not compact. Why? Because the set of rational numbers Q is dense and, of course, countable. Okay, so let us go back to the definition. If we take epsilon equal 1, then 1/2, then 1/3, etc., and the definition of total boundedness. For every epsilon, we can find finitely many balls that cover A, or X, the space. Okay? So call the space X. So this is the precise definition of total boundedness. So X is covered by a finite union of balls with radius 1 over n. And this is true for every n. So when n varies, we get a sequence of finite sets. So I call the finite set capital AN. So I have a countable collection of finite sets. Okay, now if we take capital A to be the union of all these finite sets, what do we have? This is, of course, countable, not necessarily finite, but it's countable because it's the countable union of finite sets. Okay? And second thing, if we take an arbitrary element small x in the space, then its distance to A is less or equal than its distance to AN, because AN is contained in A. Okay, so when the set gets bigger, the infimum gets smaller, okay, not the other way around. And now the distance between x and AN is less than 1 over n. Why? Because if x is in capital X, then x is in some ball. So the distance between x and some element, small a in AN, is less than 1 over n. But this is the infimum. Okay? So this is also less than 1 over n by construction. Now, here A does not depend on n. So since n was arbitrary, if I let n tend to infinity, then I get dxa equals 0. But we know from second year that dxa is 0 means that x is in A bar. So we took an arbitrary element in X, and we proved that it's in A bar. And of course, A bar is in X, so we have a double inclusion. Therefore, A bar equal X, and therefore, A is dense in X. So we found a countable set which is dense. So in particular, compact metric spaces are separable. Third exercise about equicontinuity. So we consider the collection of all continuously differentiable functions on 0, 1, such that the integral of the square of their derivatives is less or equal than 1. So we have a kind of boundedness condition here. We have to prove that this collection is equicontinuous. This is actually very easy, and it's a typical examination question. This follows from the Hölder's inequality. So pick two elements x, y, and 0, 1, and an arbitrary element in this collection. Okay, of course here x and y will play the same role, so one is less than the other. So you can call x the smaller, it doesn't really matter. Okay, so by the fundamental theorem of calculus, f of y minus f of x is the integral from x to y of the derivative. Okay, this is the fundamental, because everything is continuous here. Okay, this is the rule that you know to evaluate integrals. So because f is an antiderivative of f prime. Okay, therefore, now I take the absolute value. The absolute value of this integral is, by the Cauchy-Schwarz, actually, it's a particular case of Hölder, is less or equal than the square root of the integral of 1 squared, because I can write f prime as 1 times f prime. Okay? So Cauchy-Schwarz tells me that this is less than the integral of 1 squared raised to the power 1/2 times the integral of f prime squared raised to the power 1/2. Okay, this is a really fundamental inequality in analysis. Now, the first integral here is just y minus x and raised to the power 1/2, so it gives me a radical of y minus x. And the second integral, since x and y are between 0 and 1, this integral is less than the integral from 0 to 1, because when the domain gets bigger, because we are integrating something positive here. So this integral is less than this integral, which is less than 1. So I find finally this is less than radical y minus x. Now, if I don't assume that x is less than y, it's fine, but then I would have to take the absolute value of the integral, because if y is less than x, then this is negative. So I don't need to distinguish between two cases. But if you like, this is one way of writing things. But since y and x play the same role, so I apply this. If y is less than x, then I get f of x minus f of y less than x minus y. So, and this is just the same constant, the same number here. So, by symmetry, f of x minus f of y in absolute value is less than the distance between x and y to the power 1/2. And now this is something stronger than equicontinuity and stronger than uniform equicontinuity. Actually, it's if you like Lipschitz equicontinuity. So this is easy. If you give me some epsilon, I take eta to be epsilon squared. Therefore, if x minus y is less than eta, then x minus 1 minus y to the power 1/2 is less than eta to the power 1/2, radical of eta. But the radical of eta is epsilon. So if this is less than eta, then this is less than epsilon, and therefore this is less than epsilon. Okay, so we have therefore uniform equicontinuity, which is not a surprise because equicontinuity on a compact set implies uniform equicontinuity. This was a challenging exercise. I hope you will do it someday. Okay, so this concludes exercise 3. The last exercise in this video is more interesting. We consider the sequence Fn defined by Fn of t equal e to the minus nt, but we restrict, of course, t to 0 and 1. We have to show that this set, this collection of Fn, which is a countable set, is equicontinuous on the semi-open interval 0, 1, but it's not equicontinuous at 0. Okay? So we have to prove two things. So pick an arbitrary element x in the semi-open interval 0, 1. So x is strictly positive. Okay? So we have to prove that this collection Fn is equicontinuous at x. Okay? So here we have to distinguish between equicontinuity and uniform equicontinuity, and you will see that the eta will depend on x. Okay? So we don't have uniform equicontinuity here, okay, because this set is not compact. Okay. So we take another point y in the semi-open interval 0, 1, and we apply the mean value theorem. So Fn of y minus Fn of x is equal to Fn prime of c times y minus x for some c between x and y. So c depends on x and y and n. Okay. Now what is Fn prime? If you differentiate this, you will get minus n times e minus nt. Now, why do I'm using that? Because if I find an upper bound of this, okay, then I will find an upper bound of this, right? This is the strategy. Now, this quantity actually, so therefore we can write Fn of y minus Fn of x as minus n e minus nc with this unknown c times y minus. So, and then I take absolute values. Okay, now I want to show that there exists some eta such that if this is less than eta, then this is less than epsilon. This is the strategy. Okay, the idea is, so I have to distinguish between two cases actually. If x is less than y and if y is less than x. If x equal y, there's nothing to prove because both sides are 0. So first case, x is less than y strictly. Therefore, the c by construction is between x and y. Therefore, minus c is less than minus x in particular and bigger than minus y, but I don't care. I just need that. So e to the minus c, because the exponential is strictly increasing, e minus c is strictly less than e to the minus x. Okay? And therefore, n e minus nc less than n e minus n. Now, n e minus x and x, as you know, converges to 0 as n tends to infinity, because x is strictly positive. So in particular, it's bounded, right? If you don't believe me, you can take the len. Okay? You can prove that the len tends to minus infinity, if you like. So if you like, the exponential always wins the race against any polynomial. Okay? So if it tends to 0, then in particular it's bounded, okay, by a certain constant that depends on x. Okay, I call this constant mx, and later I will show you that we can find a very simple formula for mx, but we don't need that. Just we need the boundedness. So this quantity is bounded by mx. If this quantity is bounded by mx, then also this quantity, or this quantity is less than mx. Okay, so in this case, the distance between fny and fnx is less than this constant mx times y minus x. Okay, of course, but this is true for every n. Okay, because when I say it's bounded, it means that the constant does not depend on n. But this is of course true under the assumption that y is bigger than x. So I can drop the absolute value here. The other case is where y is less than x. So again, c is now between y and x. But if I take y sufficiently close to x, then I can make y to be between x over 2 and x. Okay, and if you subtract the x, you will find that this is equivalent to the requirement that y minus x is less than x over 2. These are two equivalent actually, provided y is less than x. Okay, so y minus x is less than 0 and bigger than minus x over 2. Okay, so an absolute value is less than x over 2. So now again, since ne minus nx is bounded actually by mx, then ne minus nx over 2, because now the c is bigger than x over 2, because c is bigger than y, therefore minus c is less than minus x over 2. So e minus nc is less than e minus nx over 2. So if I take kx to be m sub x over 2, it's another constant, then we get this, again, this estimate here. Okay, so provided y minus x less than x over 2 and y is less than x. So now I just have to put everything together. If I take eta to be less than x over 2, because I need this, and less than epsilon over mx, and less than epsilon over kx, so it's less than the minimum. If eta is less than the minimum, and x minus y is less than eta, so I go back to this condition or this condition, then fny minus fnx will be less than epsilon. Okay, and this is true for every n. So we see here that the eta that I found depends not only on epsilon but on x. Okay, so I need to ensure all these two inequalities. I need to have this, and I need to have this. Okay, so this proves equicontinuity at x. Okay, and this is, once again, it's not uniform equicontinuity. Now remark, we have a simple formula for mx. Actually, ne minus nx is bounded from above by 1 over ex. And of course, this is something positive. So you see that as x tends to 0, the constant becomes bigger and bigger. Why this is true? This is because we can prove this fundamental inequality. Te to the minus t is bounded from above by e minus 1 for every t positive. How do I prove that? This is very elementary. One way is to consider the function te minus t and study its variations. So how do we do that? We find the derivative. The derivative, if you compute it, this is a product. So we get e minus t minus t e minus t. So we can factor by e minus t. And now if t is between 0 and 1, this is positive, and therefore g is increasing. So it has a maximum value at t equal 1. When t equal 1, we get g of 1 equal e minus 1. So this proves this inequality. So in particular, if instead of t I put nx, I get nx e minus nx less than 1 over e, or e to the minus 1. So when I divide by x, I get ne minus nx is less or equal than 1 over ex. Okay. Therefore, we can take mx to be 1 over ex, and k over x, same thing as mx over 2, so it's 2 over ex. Okay. Therefore, the eta can simply be the minimum between, because now actually epsilon over kx is less than epsilon over mx. So the minimum is just this 1 over k, which is epsilon ex over 2. So the eta can be taken to be the minimum between epsilon ex over 2 and x over 2. Okay, so once again, we see that eta depends on x. Now, why don't we don't have equicontinuity at 0? So we have to negate the condition. Okay, so let us evaluate fn of x minus fn of 0. If you go back to the definition, you will find 1 minus e minus nx. Of course, this is positive, because it's an exponential of it. So the exponential is less than 1. Okay. And so I have to prove that this cannot be made less than epsilon. So it's bounded from below by a positive constant. The positive constant will be taken just to be 1/2. Okay. Now let alpha be any positive number between less than 1, and take x to be alpha over 2. And now, since e minus n alpha over 2 converges to 0, then in particular it's less than 1/2 for n sufficiently large. Okay, now, so this is e minus nx, same thing, less than 1/2. And therefore, 1 minus e minus nx, so if you subtract e minus, so minus e minus nx is bigger than minus 1/2. When you add 1, you get that. And so this difference is bigger than 1/2. So I proved, what did I prove? I proved that there exists a constant, which is 1/2, such that for every alpha, now it's enough to prove that for every alpha less than 1, as you may check, because if this is true for every alpha less than 1, it's true for every alpha positive. It doesn't really matter. So for every alpha, we can find x, which is alpha over 2 in 0, 1. And we can find an integer. Actually, there are infinitely many integers. Okay, just take the one of them, such that now we have x minus 0 is just the absolute of x, which is just alpha over 2, and it's less than alpha. And the distance between their images under this n is bigger than epsilon. So this negates the condition of equicontinuity at 0. Okay. So this concludes exercise 4 and this video. In the next video, I'm going to solve exercises 5 to 8. So thank you for your attention and see you next time.